Today I want to talk to you about circular motion, and more specifically, vertical circular motion that you see in things like Ferris wheels. I'd like to talk to you about the forces at the top and the bottom of a vertical circle. When you go to a restaurant today, the conventional way of carrying a tray is to use one hand or two hands to hold the tray. A server has to be very, very careful not to jostle the tray, or of course the drinks will spill. What I have here is a plastic tray, very slippery, and two very full glasses of water, dyed red so you can see it. If I walk the conventional way to serve these drinks, they're very full without spilling a whole bunch of drink all over the place. You can see the water on the tray. The Greeks, or some people would give credit to the Turks, had a different method for carrying their or serving their drinks. Is they would suspend the tray from their hand, like so. Now what I'm going to do is fill these up to the same level that they were before, and place them on the tray. And then I'm going to move around with this, and I want you to observe how nothing spills. So I can walk down anywhere I want, and they will swing around happily, nothing spilling. And even to make it more exciting, if I came up to a table and I said, hey, here's your drinks, and you'll notice that everything's just fine. I can spin it around my head, back and forth, and as long as I don't jostle something, all the fluid will sit in the glasses. The Greeks had a very effective and certainly an exciting way to serve drinks. How does it work so well? At the very bottom of the vertical circle, this is the water. It must accelerate towards the center of the circle. The force of gravity is on the water is straight down. There has to be a second force on the water that causes it to accelerate upwards towards the center of the circle. That force many people feel is centripetal force, but it's not. Centripetal force is a resultant force. It's never shown on a free body diagram. What it is the force of the glass pushing up on the water. You'll note that that force has to be a lot greater, indicated by the length of the arrow, than the force of gravity, because the net force must be up, causing the object at that point, the water, to accelerate up. In fact, the centripetal force in this situation is equal to the force up minus the force of gravity. At the top of the circle, we have a different situation. The force of gravity is acting downwards towards the center of the turn that the water is making. In fact, it is supplying some of the centripetal force. But I swung the thing so fast that it wasn't supplying enough. I made sure. And so we had a second force on the water, which was the force of the glass pushing down on the water. And so I'll call that force down. In this situation, the centripetal force is equal to the force of gravity plus the force down. I hope you understand vertical circular motion a little better now. Obviously, the Greeks were onto something. They must have understood their physics.